So Bob, just to recap, I put an equality there instead of an approximation symbol. And that represents all those terms, Bob. Were you listening last time? This is all the terms from the Taylor series approximation, all those things I did last time. And I claim, if you really look carefully through the Taylor series expansion, you'd find that the term goes to 0. That's like 1 over square root of n or something, or in other terms. And if you take it and divide by n, it's summable. And that's how you can get away with murder. Okay? All right, so that'll be just for your midterm, Bob. That'll be on the exam. So anyway, so here's something. It's not a waste of time. I'm going to go and tell you, if you looked at another book, how they would analyze this, because we'll use it next lecture for convergence of the algorithm. Oh, nah. Because this is actually, I'm ad-libbing completely. So here's a trick for both ODE and diffusion. I'm going to do this today very briefly for Zn. I'm going to do it much more carefully next week for the process, for the parameter process itself. So let's, do we have, so the only trouble is I want a symbol for this. Let's call it, well, we already have that Z there. I'm going to just use a lowercase z for the hell of it. So what I'm going to do is I'm going to define T0 to be 0 and Tn to be the summation k equals 1 to n of alpha k, where here we're taking alpha k to be 1 over k. So the reason I wrote alpha k here is just that in general that's what you do. You take whatever the scalar gain was, and you take its partial sums. And this is a new time scale for analysis, is what it is. Why would I do that? Take a look. I've got dz is dt times something. All right, that there is, so 1 over n plus 1 equals, all right, dt n plus 1 in quotes. You know. Right? If I define this as partial sums, I take a difference of 2 terms, I'll get one of the terms. That's all I'm saying. So this looks like a difference in z is dt times some function of z and some noise and something that's just ephemeral. I mean, it just disappears. All right. All right. Then what we will do in a simpler case, and what they do for this case, is you define z of t. So that's supposed to be a lowercase z of t, and that's a big capital Z. That's equal to capital Z of n plus of n if t equals tn. All right. Big deal, right? The point, though, is that this thing is moving very, very slowly. It's like as n goes up, it's like log n. So moving very, very slowly, you know, in the time in t here, as opposed to n. You know, here n 1 step at a time. You know, I mean, you know, as n goes up, this moves very slowly in time. You know, Tn evolves increases very slowly. And then everywhere else is by piecewise linear interpolation. All right, and so that's just to get a continuous function of time. And you can then say, well, dz equals blah times dt, and I can sum both sides, and I will get a I'll say quote unquote ODE approximation. What I'm going to get is, I'm going to get z t plus t equals, and I'm sorry, I should use the same parentheses. So that I said, I'm going to sum both sides. And when I do that, I get a sum of things times dt. That's a effing integral, right? And now I got to be careful, because the thing is that this is like white noise, and it's kind of big, right? I mean, this is something nice. We think this is like something reasonable, and this thing has an n plus 1 times it. It's like this white noise that's quite big. Now, of course, there's a 1 over n here, so there's a square root of n over n. There's a 1 over square root of n in it, but we're not discounting it in the same way. All right. So what you got to do is you got to actually go and say, well, fuck, it's plus plus, I'll just write it like this, b of t minus, or t plus t. All right, so this annoying term here is right there. And this thing here should be clear. I mean, it's a definition of an integral. You know, this is you know, basically dt times something. It's definition of an integral. So there's some error bits will come from approximating a sum by an integral as well. You know, so there will little bits of this will come into here as well. This is the part that's beyond the scope of this course. But if you take a bunch of nice uncorrelated sequences like this and sum them up, you get a Brownian motion. All right, and that's something again beyond the scope of this course. But if you look at windows, if you look at little t getting large, you can. There's what's called a functional central limit theorem. And that's outside the scope of the course, but you should know about it anyway. So FCLT, functional central limit theorem. And so B is a Brownian motion. And you know, and you can imagine its characteristics. It's going to have, you know, covariance properties related to what we talked about before. All right. All right. So this is what you'll find in the books. They'll say that they don't actually do the Taylor series expansion exactly like I did it. They don't stop here and take the covariance of both sides. They go and say, see, look, by the functional central limit theorem, I can get a diffusion approximation. And so in a way, they get a lot more because they get a statistical approximation of the whole thing, not just the covariance. But an approximation like this doesn't give you the covariance. It's, you know, this approximation is in some weak sense, so it's hard to compare. So anyway, so why did I put such a long answer to your short question? Partly, it just was right there. Once you said all this, I also wanted to point out something else, is that this is how you deal with the non-correlated case, the case where delta is actually correlated. You know, and so what you find out is that from this analysis, what you find out is that you do something like this. I mean, to replicate what I did before, you can't just square both sides and take expectations if that's correlated. You know? And let's be consistent. You can't just square both sides. Because I canceled cross terms last lecture in order to get that. And what you find out is that what I called sigma delta before is no longer the covariance, but the asymptotic covariance. You find some realization of delta on the infinite interval from minus infinity to infinity. You construct some stationary version of this whole thing. And that's the covariance in CLT. All right, and so what's happening is you've got this weird sort of linear system, and driven by this sort of not white noise anymore, it's correlated. And it turns out it's not its covariance anymore, but it's central limit theorem covariance that's important. And that's how there's a central limit theorem for delta. There's also what's called a functional central limit theorem, where you can get sums like this approximated by Brownian motion. All right? Way outside of the course, but still worth saying. I mean, especially since a lot of algorithms, this fails in a lot of algorithms. It's really important to know that's not the right covariance if you want to understand performance. It's that. Luckily for Watkins, that's the right thing. But for TD learning, for Watkins, you can just look at the covariance, because it is uncorrelated. For TD learning, it's not. You have to somehow estimate this monster. And I think the lecture notes explain how to estimate that. I think the last version does. I don't know. I won't make you do it, though. This for your records. All right?
The Brownian motion comes from the term?
Yeah, that's right. I mean, it's clear where this came from. It's just like, basically, I'm summing up Z of T dt. Yeah. And then if you pick up a book on, by Tom Kurtz or something on stochastic process approximations, it's a standard result that under some really minor conditions, you take a sum like this and do this sort of time scaling, then that sum becomes approximated by increments of a Brownian motion. It's really, really nice. So it becomes a stochastic differential equation. Yeah, well, I mean, it's got independent increments. Yeah, so it's correlated. I'd just like to say I'm summing. So the B of t is approximately a sum. And the sums of these guys are correlated, the partial sums. Right? It's increments that are uncorrelated. That's what's really cool. I mean, we start off with something correlated, and the Brownian motion is uncorrelated in the sense that you know. All right. Again, this is outside the scope of the course, but you got the broad picture? Yeah.
I have one question.
Yeah.
Isn't Brownian motion same as a random walk?
No, it's a continuous time analog of it. It's Gaussian, and it has independent increments and zero mean. Yeah. So it has all the properties of a partial sums of IID zero mean random variables.
It's just infinite variance?
No. It's Gaussian. Yeah, so it's finite variance. It's variance. The variance. We shouldn't spend too much time on this, but
Okay.
but the covariance of B of t is sigma delta times t. So the covariance blows up with time. But remember, it's approximating a sum. And this is stabilizing. Remember, there's z of r here. So you think, oh shit, that's blowing up with time, but this matrix here is stable, so it's much easier to write this as, we can't spend any more time on this, but I'll give it one more thing. It's like z dot equals a plus 1/2 I z plus b dot. So for physicists, they do this all the time. There's no derivative of white noise, of Brownian motion, but you pretend there is all the time. And it's a standard physicist heuristic. And you can imagine I've got a stable linear system driven by white noise. It's going to have a nice properties. And that intuition is correct. All right. Is this a continuous time version of that? So the fact that as capital T gets large, this covariance blows up, doesn't matter because this is forming a huge contraction part. If Z blew up, this would pull it back in. All right. So I think we should say a few more things about how to apply this stuff for Q-learning. So there's all sorts of, especially because of Marcy, who's in the room. I had a wonderful question from one of you who's here this morning, and we will resolve your concerns. Okay. And the thing is, I was going to tell you why a particular choice of A is optimal, and I don't think we'll have time. I think I told you what it is. Maybe next week I'll explain why a particular gain, matrix gain, is optimal. I think we'll be out of time today. I'll give you tools, and then we'll discuss why later. Yep.
Q-learning out of the algorithm studies does not require a model to know that the system dynamics.
That's why people are in love with it, exactly.
Okay.
That's the miracle of Q-learning.
Is that the only one that is model free, or are there other algorithms?
Well, the thing is that TD learning, they say, is model free, but then what the hell did you do with it? I mean, once you learn a value function, what do you do with it? I mean, if you want to apply policy iteration, you need a model. There's something called SARSA, which is intended to improve the situation, and which I don't think I'll talk about. It's very much like Q-learning. So improve the situation. So TD learning is model free, but all you're doing is learning a value function for a fixed policy. Okay. Suppose you want to apply policy iteration. It seems like you need a model to perform the policy improvement step. Okay. So there's something called SARSA, which I don't think we'll have time to talk about, which is something in between TD learning and Q learning, which is meant to resolve that. You learn something like a Q function, and that allows you to do an update. So that's a model-free approach. So SARSA, which I haven't defined, which is a very close cousin to Q-learning, are truly model-free, with the caveat that in the homework it's not model-free because you're using a nonlinear filter to generate the belief state. What do people do in practice? They come up with some hack. They say the past 10 observations and the last 2 inputs, that's my belief state. It's Markovian. Believe me, I'm a genius. Okay, and then they run Q-learning.
Small little state space that might work.
Yeah, I think people claim it works. Sometimes it does. I don't know. I mean, the thing is, it's a beautiful tool, and sometimes it works and sometimes it doesn't. And the range of applications where it works is not really ever going to be quantified because we're never going to have a universal theory for optimal control that always works. It's just we've got a big set of tools now, and we can play with them and try to make them work. But let's just pick apart. Let's pick apart Q-learning in the fully observed case, so we can understand what we're doing. This is by far the most important question to answer. And I think maybe some of you know the answer, I don't know. But anyway, let me write it down. So remember our goal. Okay, so I mean, maybe that's the wrong place for the, that's the wrong place for that line. Okay, so we're looking for solutions to that equation, all right? You know, and I'm not going to bother with what that is. I mean, whatever that is, you know, you can choose this as a moving average of the basis functions, or you can do all sorts of different things. Whatever it happens to be, this is it. And for now, I'll assume, let's just assume it, that yeah, why not? Let's be concrete. As far as I know, I mean, I don't, Aditya, does this exist in the literature, the way we're using it? So, a Q of lambda learning. This was defined just for the Watkins algorithm, without any motivation. But in this class, we'll call this Q of lambda learning, where you take your sequence of basis functions, these are d-dimensional, pass them through a first-order low-pass filter, defines the eligibility vectors. All right? Now, the reason I said, let's be concrete, is that this doesn't depend on theta, so it'll be easier for me to talk about, you know, about what A is. Now we can dismantle this, right? I'm going to, I mean, what is A? You know, this is the thing we said we're really concerned about, because we want the eigenvalues of A, the real part, to be strictly less than -1/2 for a finite variance. You'll find an asymptotic covariance as we defined before. And you know, if this is not satisfied, you can end up with really slow convergence. So let's tear this apart. Let's take a linear parameterization. Okay, so I've got a size, a d-dimensional vector of functions of x and u. I take its dot product with the parameter theta. That gives me an approximation of the Q function. What's that?
Covariance? Finite what?
Asymptotic. I said covariance and I realized, let's be precise. As I defined last time, the asymptotic covariance. Now, you think I'm cheating. I'm talking about the fully observed problem, but remember, you are looking at a fully observed problem because your xn is really yn and bn. It's the belief state. And the cost function is the cost function. I mean, you're nodding your head, but some people need to be reminded that we've declared that every optimal control problem is fully observed if you choose the belief state as your and yn as your state space. All right, so we can make this look linear then, because I've got one term that doesn't depend on theta. All right, so there's a gradient here, so this first term is not going to matter, you know. So my definition of A, I'm taking a gradient with respect to theta. So this first part, when I take a derivative, it'll disappear. So it's not important from variance analysis. It's obviously important.
Usually the linearity property of expectations is where
Yeah, I'm about to take the expectation of the rest. And I'm going to take, this is just a scalar function. It's really helpful to put it on the other side. It's just a scalar. I can move it on the other side. You'll see why in a moment. It looks like I'm wasting chalk. I usually don't do that, but I'm slowing myself down. All right. And now what I'm going to do is, this is a linear function of theta. Nice. You know, I mean, if this whole thing were linear, it'd be pretty easy. That's not, because I'm taking a minimum, to define q lower bar, I'm taking a minimum over u. This is a concave function of theta. Because it's a minimum of linear functions. It makes it concave for any x n plus 1. All right, let's go back and check. Yeah. So this is a dot product, it's linear. To get a lower bar there, I take a minimum. And if I take the minimum of this over u, I will get a function that's concave in theta for each x. And I take minimum of linear functions, I get a concave function. All right, so let's just write this down then. So this is equal to the same thing. And expectation of zeta n, what I'm going to do is this. I'm going to write beta times something. I'm going to take this whole thing as a dot product with theta. Now the first term's obvious. It's already defined as a dot product. All right. To write that as something dotted with theta, well, it's psi dot theta. I just said that. All right. But this is 2, because this is just, I take psi and plug in that minimizing input. I ran out of space, did I? No. There we go. Let's just stare at that and try to figure out what I meant. What do I mean by phi theta of xn plus 1? Not optimal though, yeah. I'm writing down phi theta for any theta, and I need to do that because I have to take a derivative in the end. So not optimal, yeah. But your guess of an optimal, yes, yeah. So I'm going to define phi theta of x to be equal to the argmin, yeah. So by defining it for any theta, define the policy. If I thought theta was optimal, theta was theta star, this would be the policy I would apply. Right? And so by taking that policy and plugging it in here, I get that q lower bar. Now, I'm not doing much, but that gives me my A. I'm going to just write this as minus B plus A theta. And you can't do this, but I can. Take the theta outside. I typed this up this morning, so I'll send you revised notes. All right? There was a theta here. I just took it outside the expectation sign. Now, yeah, A depends on theta, but let's think about this a bit. I've got a finite action space, and I'm going to be differentiating at theta equals theta star. If this argmin is unique for theta star, then if I perturb theta a tiny bit, it'll still be unique. You know, if this policy is unique, for theta star, so I write equals argmin. Suppose that for every x, there's a unique minimum. Right? This is continuous. If I move it a little bit, it'll still be a unique minimum. It'll be the same value of u.
And that's because u is discrete?
Because discrete, yeah. If you were smooth, I would have to maybe differentiate or something. But if you lived in a smooth space, it was an interior minimizer, I could use the fact that it's zero sensitivity. So I can get away with things even if it's not discrete. You know. It's actually, I mean, you can get away with, it's the concavity you can actually take advantage of in general. The fact that we can talk about subderivatives and stuff. I mean, But forget that, forget that. That's right now in a finite action space. Do you believe me that with theta equals theta star, for every x I have a unique minimizer, that if I move theta just a tiny 10 to the minus 10, it'll still be unique with the same value? Because it's continuous. Being minimum means I'm strictly less than any other u for each x. And that's why, even though this depends on theta, its derivative with respect to theta will be 0 if the policy is unique.
The reason why you can take the theta out, the expectation, is because
Oh, it's just a vector. It's not random.
it's a deterministic thing.
No. This is f of theta. This every step here. It's not random. I took any theta in RD.
Are we still enforcing the theta equals theta star that you were?
Well, it's only 0 if theta equals theta star. But in order to compute this derivative, I need to know f of theta in a neighborhood of theta star. I need to compute it. So this is true. So this A, this is A equals really A of theta star. Theta minus theta star small. But this only works if it's unique. Otherwise, I get into trouble. All right, and again, what I mean by unique is that for every x, there's a unique minimizer. There's no ties. And generically, that's usually true. It's really kind of fragile to have two guys that are optimal. I'll change my cost function by 10 to the minus 10 and make it true. It's really, you can make it true just with a little.
What did transpose go now? Are you going to take outside?
Oh, no, Missy. I just said that this is a dot product. If I take the theta back inside, the transpose is there. I just put it there. All right, here there's a theta transpose psi. I should have written psi transpose theta. Same thing. Okay. You know what I mean? If I was going to make it, so yeah, flip it around. Same thing. All right. So there you have it. So there it is. You're all clear. That's the answer. There's A. Because I'm saying now that locally it's just a linear function of theta under this condition. This equality holds if theta is sufficiently close to theta star, and so therefore this is actually linear in a neighborhood of theta star. So it's really easy. That's one observation.
Did you plug in theta star? If you plug in theta star into the expectation, then what you will get is.
No, it doesn't matter. No, I'm just every one of these steps is just true. The only thing I did here is I just had a different representation for Q lower bar. That's all I did. And then I argued, and I hope you agree, that if this is unique, then by perturbing theta, I don't change this policy. It'll still be the same thing. For a finite action space, I move this a tiny bit. I don't change this function very much. I'll still have the same minimizer.
Should we expect to see negative b plus a of theta star times theta to be equal to 0 from now?
For theta star, yes. We know that. Absolutely. But that's not what so you're absolutely right. So we know theta star is absolutely, we don't need the uniqueness. That's always going to be equal to A inverse theta star B. That's why I put the minus sign here. So that's why I made that definition. So you're absolutely right. That's the optimizer. But in order to